Okay, so it is my great honor to introduce Professor Kim from Seoul National University. She is the head of the 3D Vision Lab at Seoul National, and she's also currently a visiting scholar at UCSD, and she received her bachelor's at Seoul National and PhD at Stanford. So before joining Seoul National, she was a senior research scientist at Korean Institute of Science and Technology as well. So today she will be here to talk about functional 3D vision, and I'm very happy to hand over the stage to them. Thank you.
Thank you very much. Pleasure and honor to be here, and I'd like to thank Professor Kang Lee for giving me this wonderful opportunity. And I was actually thinking about more like casual talk, and actually I was intimidated by what happened this morning, but I'm not devastated. So hopefully let's see how it goes. So I'm going to talk about synthesizing and reconstructing 3D scenes, and I run 3D Vision Lab, and we handle a variety of topics in 3D vision, and I will talk about a few of the recent progress in this aspect. So let me start with something big. So the hype of deep learning has been around for more than a decade now. Ever since the deep learning architecture produced incredible performance for the on the computer vision technology, but I would dare say we are now entering a new chapter after the foundation model showed incredible performance on various tasks. And here is, for example, if you have a chat GPT, it scores very well on bar exam, LSAT, SAT, or GRE. So this takes years of training for human to prepare for, but those AI can do, and even normal people are really excited about this opportunity. But as a member of AI researcher, you should have noticed that these are kind of tasks that's curated for AI to perform well. So they have a clearly defined scope, and we have a large database of problem sets, sample problem sets, and we have a clear answer for each problem. So for this type of work, AI can perform well. So, great. So Hans Moravec back in 1980s had a wonderful intuition, and what's this famous quote of Moravec's paradox. So it says it is comparably easy to make computers exhibit adult level performance on intelligence tests like a GRE, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. So basically, what is easy for human is difficult for computer, and what is easy for computer is difficult for human. So whatever you do, like instinctively, without paying too much attention, it becomes very hard for a computer to learn. And Moravec at that time thought about this as an accumulation of skills from the evolution. He explained it that way. But as an AI researcher, again, we think it is possible because of the lack of data. So there are not many data which shows you how you manipulate some object like this. It gets really hard to actually make things out to such that computer can understand. So now people kind of have a good understanding of what AI can do versus what AI can do. And I think you guys already well aware of those, but I will just briefly go over one of the lists. So ChatGPT can distinguish fact from fiction, and they will have obvious inaccuracies, like it takes 9 women and 1 month to make a baby. And it hallucinates, makes things up. And if you want to assess the reliability, it can't really tell us where the information comes from. And its information is outdated. So today, ChatGPT's knowledge is known to be sometime up to 2021, but probably it's one of the easier problems to solve. So with that, basically, I would rather say the performance of AI, at least at this current form, depends largely on availability of data. And that brings me back to the point where the 3D vision can be difficult, because compared to other modalities like texts or images, we have a scarcity of 3D data. So there are flagship data sets for images, even though there are many other data sets currently available. There's ImageNet versus ShapeNet. And as you can see, you can observe a large gap in terms of number of data points available or number of categories covering or even the year that it is introduced. So why is there only a scarce amount of 3D data? This is because it is hard to generate 3D data. So you need to have some skill. You need to have a specialized software to be able to generate 3D information. So for example, if you want to build a virtual scene like this, then it takes quite amount of labor, and which boils down to money. And the slide is kind of outdated, so I think the price might be higher these days. Then how about capturing the 3D data? We are surrounded by 3D objects, so we can try to reconstruct those 3D models, but still 3D acquisition is also hard because not many people have access to 3D sensors, and there are many different kinds of sensors and many range of price for that. So there's laser scanner, LiDARs for autonomous driving, or RGBD scanner, or time of flight sensors, or you can even use images to get a multi-view stereo output for structure for motion. But whatever sensor you use, you usually have to have multiple scanning times, and then you have to merge them together, register them together, and convert it to some format that computer can understand was more appropriate for the purpose that you are using for the 3D models. Yeah, so 3D acquisition is hard, and you are going to suffer from noise. Whatever sensor you use, you're going to suffer from noise. You're going to have occlusion and complex missing holes that you have to do post-processing with another skills. And another challenge with 3D vision is the format is all different, and not all of them are also mutually exclusive with one another. So people use hybrid format, and especially neural network shows very interesting performance when combining with one or more of the representations, and these are becoming very popular, and new representation is always emerging these days. And we saw many of them a few days ago as well. Okay, so the format of 3D data depends on how it is created, whether it is scanned or it is created from a 3D software, and what kind of purpose it's trying to solve. I mean, what kind of purpose it is trying to serve. Okay, so I just listed a bunch of different difficulties regarding 3D data. And as a 3D vision lab, we are focusing on two kinds of problems. One is about 3D generation, and the other is about 3D reconstruction. And I'm gonna point out some of the recent progress in each aspect today. So I'm gonna briefly talk about 4 works, as you can see. So let me start with the 3D generation work. And for the 3D generation, at that point, we were fascinated by the power of deep learning. So we wanted to make this neural network deeper, so you will get more richer information. But if you extend the 2D image, at that point, network was getting deeper and deeper and deeper and getting better performance. But if you want to build a neural network that has a very deep structure, the 2D images have a quadratic size of memory and computation, whereas 3D you have a cubic size. So we cannot just extend it with another dimension. So we applied some technique to get away from that. And so the work I'm going to introduce today is called generative cellular automata. So instead of trying to have a dense convolutional network to represent the scene, we use some characteristic of 3D shapes to get better or efficient with memory and computation. So one property is sparsity. So if you have a 3D model, and if you have a lower resolution of a higher resolution of model, you tend to have a more sparse amount of data occupying the space. So we wanted to utilize that to be efficient with the 3D data. And also we observed that the shape tends to be continuous. So there is a connectivity. So instead of trying to search the entire space with a dense probes, we wanted to go over and grow from the existing shapes. So those are 2 motivations. And with that, we applied the cellular automata. So cellular automata is basically, the idea has been around for a while, but basically you are having homogeneous chrono. So for example, if you apply cellular automata to generate images, you have exactly the same chrono for entire space, but depending on what neighborhood you have, you're going to transform yourself in neighborhood. Then after multiple iterations, it's kind of similar in spirit for diffusion modeling, but at that time diffusion was not that popular when we were developing this. So we have temporal accumulation of this transformation, and such that we will eventually get a better reconstruction of the entire image. So here is an example of what cellular automata can do when it is trying to generate 2D images. And we apply similar technique in 3D, but utilizing the sparsity and connectivity. So here's the idea. So each shape is represented as a state, and we have binary occupancy grid on 3D space. And that is state. So state is the shape. And we build a Markov chain such that homogeneous kernel tells you how it can better go closer to the shape that we want by having iterative Markov chains. And so there is temporally homogeneous and also it is spatially homogeneous. So for each step, we have the occupancy grid, and for better visualization, it shows a 2D grid. And wherever it is occupied, we take a look at the neighborhood information and then get the probabilistic distribution of how it should be transformed, or how what the occupancy would be for the immediate neighborhood of already occupied voxels. So we have an individual prediction, as you see over here, then merge them just simply averaging each other. And we have a probability distribution of how the shape would be for the immediate neighborhood of already existing shape. And we sample from there and start from the new state. And each of this occupied cell will become another source of the transform. Okay, so basically we formulated the problem with a local transition because we wanted to utilize connectivity. And instead of actual dense CNN, we use sparse version of CNN so we can become more efficient with memory and computation. Okay, so that was basic idea. And because we have somewhat probabilistic formulation, this could be sampled slightly differently, and then the later stage can transform differently as well. So that means we can have diverse shapes. So if we have a same input, we can have quite different but yet nice looking shapes. And at that point, we achieve the best results with the existing database. And we have given the input, we are transforming to have a complete shape. And this input can be anything. So if we just let this input to be a single cell and then grow from there, and we can just do shape generation like this. And because it is, again, probabilistic, this shape can be different for every time we run it. So we can, with the same kernel, but we train kernel per category. So for the same kernel, we can have a diverse shapes in general. And the shape was indeed sparse, so we could use only about 2% of the voxel to generate complete shape according to the data set. Okay. And we also did a follow-up work from this because it was binary occupancy. And if you take a look at it, it was not at the quality that you would put it in a virtual space. So we wanted to have a continuous surface. So we have a similar idea, but extended this with an implicit surface. So neural implicit fields. Given the input, we are going to generate output with a similar technique, but apply neural implicit surfaces. Then we will get still diverse shapes as you see here. So for example, the sofa is a little bit different for every runs. For this extension, we use deep implicit fields, which can take an input of XYZ coordinate and output the signed distance function or unsigned distance function. And we use local implicit field. So local implicit field is basically for each cell, we have a latent vector, which can be decoded with a shared decoder to a continuous shape. So instead of having binary occupancy, we are having a latent shape included in there, a latent vector. And we apply same cellular automata to get a continuous shape. So basically, and we also want to utilize sparsity. So whenever the cell is occupied, we have a latent code, which can be decoded to a continuous surface. Okay. So idea is similar, so we can shape, but we have latent vector instead of binary occupancy. But because of the probabilistic formulation, we notice we can have, even though for low probability, some noisy points can be sampled. So after we have somewhat complete shape already, we instead of sampling from probability, we just take the maximum likelihood estimate of the cells, then we get complete shape, which can be decoded back to a continuous surface. Okay, so we could apply this for shapes, but what is more interesting, in my opinion, is we could handle the entire scene, because each cell can represent larger scene with a continuous surface. So we run a single loop. I mean, we put everything in a single computer for scene scale geometry and get output of continuous surface with probabilistic scene completion. And we have some numerical results with the scalability regarding the scene completion. Yeah, so that was about what I wanted to talk about in the shape generation. So we proposed kind of new formulation of generative cellular automata, and we think this is scalable and it could be extended into diverse yet continuous geometry. And I think we were among the first which can tackle the problem of scene completion, continuous scene completion in probabilistic way. Okay, so that was the first part that I wanted to discuss. Is there any question for this work? Yes?
How do you check the shape you generate is actually new and not memorized from the training sample for the first work? Did you look at some nearest neighbors from your training shape to
Yeah, so
double check?
for shape completion, we had a ground truth, so we can compare the distance between them. And for complete generation, they have some metrics. So there are, do I have a here? So you get a distribution of shape and get the distance to the nearest neighbor, and based on those distances, there are like several metrics that we included in the paper. So like mutual information and the mutual distances, what is closest versus what is farthest among the existing database of the training category, something like that.
So they are different, right? I'm not sure.
So there are like various different kinds of metrics, and we use 3 of them. And for each of them, we had a better performance in general.
Do the cells have some kind of positional encoding? So do they know where they are in an overall scene? Or
Here, no, we didn't. We just
Okay.
have a cell and have a neighbor. We use the convolutional neural network. So we have a neighborhood information, and because it's deep, it kind of looks at the bigger neighborhood as well. But the output is only through to the immediate neighborhood. That's it knows relative position relative to the neighborhood, so we don't have an absolute coordinates for the.
okay, and the neighborhood is like it's isotropic.
Oh yeah. Yes.
Sorry. In most of the examples that you showed, those are fabricated objects like chairs, airplanes,
Yeah.
cars.
Those are from ShapeNet. Yeah.
Were you ever able to give it like a tree or a bush or something that has a lot more like fine-grained geometry that maybe like, doesn't have as much smoothness and it's more.
Yeah. That's a very interesting question. First of all, trees are really hard because many of these cases we assume there's a volume in the 3D geometry, like say people prefer like water-tight surface or something like that. And trees have leaves, and it's very hard to define the shape in conventional way, but still it is doable, I think, because we also apply the same technique for unsigned distance field, so it doesn't necessarily have to be water-tight surface, and you can probably generate thin surfaces. And also we have a student who was first author here. He also tried to do similar technique for a larger scale scene with autonomous driving, and he did construct trees and buildings, and because it is scalable, you could do for city level construction as well. Yes, but it's difficult, and it gets even harder if we want to assess the quality and quantitatively for trees or bushes. Any other?
And you just one more question. So is it a diffusion-like process where you need to decide how many steps?
Oh, yeah, it's
want to
similar,
have-
but we say it infusion process because diffusion is kind of noise, it put noise in and we get the backward process. But what we do is, I didn't put too much detail on it, but here we have a ground truth shape and then we kind of force the shape to go to the ground truth shape by injecting probabilistically the ground truth shape and then force them to less noisy steps. So it's kind of opposite or similar in spirit in diffusion training, I would say.
And so in the example that you're showing, there would be like 100 steps or something, or? 50.
50?
Yeah, 50.
Yeah.
50. Okay, 50.
I don't know
okay,
the
good. Great, yeah, just
shape generation, and we were also. And for next, we switch the gear and I'm gonna talk about texture generation because texture is something that makes things more realistic. Okay, so this is a work presented a few days ago. So it's called texture, and we say we are doing scene stylization. But if you say stylization, there are some previous works which tends to put styles on the entire scene. But it's something like you want to put a Van Gogh style or Monet style for the scene. But in that case, they don't really care about the scene structure, but just have a color distribution that or like a details of texture that's similar. We want the opposite. And also there's also prior work which try to stylize a single object at a time. Then here they do have some structure, semantic structure that's analyzed or captured by the network. But when we try to stylize a highly structured object, something like that, which requires clear part boundary between different parts, then it didn't produce as amazing results as other examples that's included in the paper. And we were tackling something like this. Okay. So after doing 3D stylization, hopefully we can create a virtual space because there are many 3D models for virtual spaces, but not that many 3D models with a realistic texture on it. So we can utilize those by having more realistic texture, and hopefully it can be used for content generation for AR and VR, or we can even do interior recommendation. However, there's not that kind of 3D data available. I mean, there are many 3D geometric data, and sometimes they have texture on it, but it is hard to process those data, and also they are usually having a texture parameterization, which have a complex map from 3D surface to 2D surface, and also they don't have a same data representation to start with, and it will be very expensive to compute those stuff. And we wanted to get away from that with some small techniques, and I'm going to talk about this in more detail later. So the setting is following. So we have a 3D scene and we want to put colors on it. And by stylization, we want to have a user intent for which kind of style we want. And it's given by image and text. So you have a target image to have a similar color distribution. And we have a style text. And to give you a little bit of spoiler, the target image, for the target image, we have a loss that try to have a similar color distribution by comparing the color histogram. So we are gonna enforce histogram loss for target image, and for text, we are gonna enforce clip loss. So we are gonna get the distance from the rendered 3D scene versus the input text, and then try to minimize those distances. Okay, and the output is something like this. So given the input, here is the brief pipeline of the entire network. So we first handle the structure separately. So by structure, what we mean is walls, floors, or ceilings. This is because we are using two-dimensional rendering to enforce some consistency on 3D. And by using 2D losses on top of 3D, they treat those like big walls like a canvas. So if we want to have some realistic scene, they're gonna draw the scene right on these walls. So that's not something that we really wanted, so we treat this separately, and we also assume that we already have a class labels. So if we know the classes like walls or floors, we will just treat it separately and use a material library that's already existing there. So we didn't, that's not our contribution, but we use the differentiable material library to match those classes. And then for objects, we first pre-process the object to have individual parts. So that's pre-processing. And then we have two stages of stylization. One is base color assignment, followed by detailed stylization. That's the big picture. And I think what's more interesting is part discovery throughout the process. So basically, we want to have part, but it's different from any of the existing part database. So there is some 3D part database, but they are more like functional parts, which are handles, which are doors, something like this. But we want something different. We want to have a part that has to be assigned with a similar material in general. So for example, in this chair, we have a chair handle and then legs with a similar colors, but those kinds of information is usually not in the database that's already existing. So what we want to do for that, so we first do create an over segmentation of the 3D mesh. And those who are familiar with super pixel, we call it super segment. So we have an over segmentation like this. And then we optimize for the color for individual segment. So we have a one solid part, a solid color per segment, such that it will have the rendering of the colored object will be close to the class label bed in clip embedding space. Okay, so we are going to change the colors of the individual parts such that the rendering looks like a bed in clip embedding space. And we have a color, some kind of color combination, but you can obviously see these two colors are kind of assigned with a similar color because that will look more like a realistic bed according to the large database that clip is trained for. And these two became similar, but not really similar here, but it eventually becomes similar. So whenever the neighboring segments are assigned to the same color to get this semantic embedding, we merge those parts together. And we iterated this process not that many times, but a few times, like 3 or 4 times, and we can discover parts that has to be assigned with a similar material according to the clip embedding space, given this class label. Okay, and we have this part that we can greatly reduce the optimizing space. We can assign different texture per part, and for this, we do base color assignment. So basically, the base color assignment, again, assign a single color per part, and we optimize for the entire scene, but we can still handle entire scene because the optimization space is quite low because we are only assigning a single color per part, and there are not that many parts. And then optimize in, again, in clip space that it looks like a realistic scene, and we also try to match the color distribution of the input image. And then after base color assignment, we additionally put more decorations or ornaments on top of it using detailed stylization. So we have part discovery, base color assignment, and detailed stylization is something like this. So we use a texture field formulation, or if you're given XYZ coordinate and the part ID and the kind of intrinsic geometry information in there, you get the deviation, slight deviation to make it more realistic. So you can introduce additional wrinkles or like small details on it, so it can look more realistic. But the optimization space is, again, it's slightly smaller because we already have some base color set. We are just adding perturbation. Yes.
Sorry, just a question. When you do the color similarity, do you try to adjust the viewpoint so it matches what your reference is, or?
We have a set of viewpoints that we are using. So we have a different, camera poses. How many images?
Single set,
Yeah.
maybe random sampling just for under set.
Yeah. So how many? Like,
5.
5 or 10. He knows. Right. Yeah, so that's about it. And this detailed synthesization is kind of more computationally expensive part, but so we do it individually for different objects, but other parts are done holistically for entire object, entire scene. Okay, so So these are types of rendering that we create for objects. And so we can, without this two-step stylization, we will have kind of blurry boundaries between parts, but we can have those clear boundaries. And I think that plays a critical role to provide a realism to the resulting texture. And we can have a different input images that will have different distribution of colors, and we can have different styles. Then style is somewhat hard to evaluate, but we have somewhat different stylization. And even if with the same input, if you run multiple times, you can have slightly different results as well. So that was the second part that I wanted to talk about. So basically, we are stylizing indoor scene, but we do not require any 3D supervision or part data set. And we have part discovery and combine it with a two-stage method and have a better looking scene, I think.
Just to be clear on the part discovery, like that's going through clip to produce a more like to do that, the merging of the different parts, like that's using clip. Is that correct?
Yeah, we're
Okay,
using
okay,
clip,
got
and we use for the clip we use a text. The text is the class label. So if the class label is bad, but would be realistic looking bad, we are enforcing laws based on that.
Got it. Okay, great. Did you find any examples where a clip would lead you in the wrong direction and any counterintuitive results for that part merging?
It was really hard to say how realistic it is, and we were actually worried by the point when we were submitting the paper that we had some human labeling, but it was highly biased toward many of the PhD students, and but still, yeah, it was really hard to like quantify how realistic or how bad it is. So I cannot recall real bad example right at the moment, but I cannot really tell that it's like universally best results that we have got.
Yeah.
All right. Okay, so that was about generation, but we are also really interested in capturing real spaces and actually perform some tasks. And this purpose of reconstruction can be different, whether you want to have a realistic visualization or whether you want to really perform some tasks. And I'm gonna briefly talk about visualization first. And for visualization, of course, the nerve is like in a state. So you only have images and you create some visualization so that you can move around within the scene. So that's another paper that presented a few days ago. It's called Balanced Grid for Egocentric View Synthesis. So nerve is great. You can have a very good rendering of an object, but if you want to get an immersive view of an entire scene, it gets really hard to train nerve. And for example, this is typical camera setup for like original nerve setting, and you need many cameras with overlapping view for combined object. Whereas if you want to reconstruct indoor scene, this is like a typical trajectory for like indoor slam or indoor scene reconstruction. So if you try to train nerve with this kind of trajectory, it can fail and it can have many artifacts. It really takes a long time as well. So you want to have a somewhat easier or casual way of have an immersive view of a scene. So this is what we suggested. So this is a panoramic camera by Rico Data. It's like around $400. So you have two fisheye lenses attached to each other. So if you just press the button, it will generate one panoramic image of the 360 degrees. And you can also take video with this. So what we did is we put a selfie stick and put the camera at the end of it and rotate it around for like 5 seconds. And you get a video, then you train nerve with this video. And you get a 360 degree of nerve. So hopefully we can capture the scene for visualization with short capture time for casual users with low cost devices and without too much expertise on 3D model. So these are type of images that we used for input. So we both tested with synthetic data and real world data. And we wanted to utilize many of the recent advances in nerve, especially the ones that has a fast converting speed, because we are having large scale scene and we want to be quick. And as many of you will know, people use the feature grid based method. So instead of trying to model the entire scene with a single neural network, you partition the space with a grid and embed a latent vector per feature. You have a lighter neural network to decode whatever you want, so you can accelerate this. And another thing that we really like is KendraRF, which is the feature grid is further vectorized into matrix vector decomposition, such that we can have an efficient memory and quickly invert. And instant NGP shares similar spirit. So basically, we want to apply this feature grid-based acceleration on this panoramic image. But there is a difference in the scene setup, as I mentioned. We are not doing inward-looking view, but we are having inside-out views. So we want to have a grid structure that better aligns with our views. So typical method use Cartesian grid for the bounding box. So they have X, Y, Z coordinate like this. If you use Cartesian coordinate to partition the space, and if this is a trajectory, and if you're looking outward, many of the spaces will not be hit by ray if it's far away, but it will be more, the ray hit ratio will be more concentrated in the middle. Okay. So what we did is we simply used a spherical grid to represent the neural network, nerve field with the panoramic images. Okay, so then we did some toy experimenting so that the ray hit ratio becomes more uniform over the entire data structure. So we are better utilizing the input data for training. Okay, and we also can increase the size of the cell when it gets farther from the view. So that's good, but for a spherical grid, if you use naive spherical grid in 3D, if you think about it, you have a high density of vertices of North Pole and South Pole. And it turns out if we just use naive spherical grid, that kind of data structure introduces artifacts on trained view. So when we try to visualize poles, there's something like this shape which kind of have a shade of the grid shape when it's projected on the image compared to what it's supposed to be. So what we did is we get rid of those pole regions and then have only half sphere that's covering equator and more regular region. We have exactly same copy and rotate it around and then put it like a tennis ball. So we have two spherical grid, but we only take a partial parts that has more or less regular angular partition. And these two shells can cover the entire angular region with not really regular, but quasi-regular partitions. And then we also do further factorization. So instead of XYZ factorization for vector matrix factorization, we are using R data phi, and that's visualized over here. Okay, so we are using similar technique for recent nerve for accelerated, but better align the data structure to the panoramic image. And there's another small technique for training. So we nerve usually is trained with a coarse to fine sampling strategy. And instead of having separate grids for coarse sample and fine sample, we have a coarse sample and then put predefined kernel on it, and then have an initialization for fine samples and utilize that to have a sampling. Okay, and then another small trick is we put environment map, which covers the infinitely far region. So even though we are exponentially growing the R, we really don't cover the R infinite. But if we go to outdoor scene, something like sky or clouds cannot be easily modeled very well. So we just assume there's a big plane for infinite region and combine that when we're training nerve, and we jointly train for the environment map. Right, so with that, so nerve is in the blue here. So, nerve, the quality of nerve depending on how long you train. So if you train it, you get better and better. And mid nerve is kind of like the best performing as far as I know. And there's so many new things, so I'm not sure about it. And it's really good, but still it's very slow in training to get the PSNR. And faster version using a voxel partition has a much shorter training time, so it's really usable. And we are utilizing the faster version with a spherical grid and then get a good PSNR for this particular panoramic image setting. So this is the synthetic camera trajectory that we use to train nerve. We use like 25 images to train the nerve. And here is the camera trajectory. And what is also interesting is sometimes cameras goes outside of the training volume, but still because the objects are kind of far away, it doesn't introduce that much depth parallax, and we can still have a okay rendering. And another thing about previous work is IMNERV 360, even though it gets pretty good PSNR, it sometimes miss a structure entirely. I'm not sure whether I point that out here. Yeah, here, the broomstick is over here, and then nerve gets this, but IMNERV 360 kind of erases this. So we notice this kind of artifacts when we are doing, but I think they also have recent versions that get away from those artifacts. Here we have a hanging collars and the lamp posts and some details of greeneries or like bushes here, and where you can get the differences of ours versus other previous. So the existing works actually does pretty good, but like you also have a video on the website. Yeah, but they're good. But you can see when you are rendering far away objects with the camera, the video quality is not as good as when they are fine-tuned for the better combined setting. We also apply the similar technique with our own data set. So it's a real data set captured from SNU, but there is a quality cap between synthetic data and real data. And we think this is because of motion blur and inaccuracy in camera trajectories, but still compared to other works, we are still quite blurry. So we have text to better show the how detail is blurred or not. So yeah, hopefully we introduced an easy way to capture holistic environment around us. You can even do it over here and then rotate it and then get the immersive view of that. And we introduced a data structure, balanced spherical grid, and achieve better reconstruction in a short time. Okay. Any questions? Yes.
So actually, so from what I understand, these spherical grids are for the outdoor scenes. We also use that for the indoor scenes, or it's just?
Yeah, we use that for indoor scene as well. Yeah.
Okay, I have a question though. So basically now we were working on this KT 360 novel view synthesis leaderboard. So just a question related to that. So, so in like autonomous driving, we have kind of very strange situation where the car is driving straight, or in lens is like a kind of very long rectangle. So, do you think these kind of feature grids would be also appropriate for this kind of task? So it's like an outdoor scene with a very where you have the background is very far away. But like it's in a, but the car is still moving.
As long as the trajectory is smaller compared to the scene you're observing, spherical concrete might be better choice for training those.
Yeah, but
I didn't really try with that.
Yeah.
You also use like a cylindrical or capsule type grid.
okay.
You set the threshold where you drop from the furthest, the largest radius bin over to the environment map? Is that a setting as an input parameter?
Yeah.
Okay, yeah.
So similar to nerve also have a setting of min, max, process. So basically, we compare against the same grid resolution for Cartesian grid as for better results for non-Cartesian. Right. So then the last part is about navigation. So nerve is just for visualization. It doesn't really get the geometry. It has some geometric context, but if you want to perform the task, you want to have a very detailed geometry. And this work is not published yet, and I'm gonna briefly talk about calibrating panoramic depth estimation for robust localization mapping. So we did a few work with the panoramic cameras because it's an easy way to get the global context of the scene. And we utilize the depth estimation network such that depth estimate. I wanted to get rid of it, but I think this is not my policy. Well, it's fine. Okay.
I was too scared.
Yeah. We are almost there, so I think we are just gonna leave it here. So, there are many network which estimate depth per pixel, as you might already know. We are gonna utilize this to actually perform the task within the scene. So if you have a panoramic image and depth estimate, and you can have an entire reconstruction of the room, something like that. We'll see over here. Even though it's noisy, we have some context. So basically, the setting is that we have a panoramic depth estimation. So without any depth sensor, just having a panoramic image, you can have a geometric context, and then we can perform tasks with robot application, for example. But because there is always a gap between training data set and deployment scenario, whenever we try existing depth estimation network, it is really cool with this data set, but if we try with the actual data in deployment scenario in our own environment, the depth estimate was not that accurate. So we wanted to get rid of this domain gap by quickly fine-tuning the network to the current setting. Yeah, so the idea is we want to get a better estimate by using self-supervised loss, which is basically built upon geometric consistency. So we can have synthesized panoramic image by manipulating current depth estimate. So it's not really accurate, but still we can use this depth estimation and then change the camera viewpoint or change the scene a little bit and then create another panoramic image and then do the depth estimation here. And we wanted to enforce the consistency between them. So that's the basic idea. And this kind of fine-tuning happens online during the deployment scenario. So you put the panoramic camera in a completely new environment, run it a few times with a depth estimate, and then manipulate the observed scene, then enforce geometric consistency, and hopefully it can better adapt to the current setting of the environment. All right, so here are actual losses. The first one is stretch loss. Stretch loss is, it is really easy to get the estimate of the ground plane. So we fix the ground in ceiling and then stretch it in horizontal way. So you have a larger room, a smaller room with the same floor. So we use several different stretch factor and then create a synthetic image based on that. So we use a depth estimate to create synthetic images and get the depth estimate and then convert it back to original scale and then enforce consistency between them. So that's one loss. And another loss is more like a geometric loss. So we have a panoramic image and then wiggle the rotation and translation of that a little bit and using the current depth estimate to create a synthetic view from slightly different viewpoints and get the depth estimate and then project them, convert it back to 3D space and compare the distances or normals of the closest points to and see how close they are and reinforce those laws to fine-tune the depth estimation network. And it turns out this was pretty effective and fast. So the gray lines are the gray dots are the errors when we perform no adaptation. And there are also many existing test time adaptation techniques, but compared to that, ours is like the green ones and ours achieve lower errors in general for many other adversaries or like noisy situations. And more accurate geometry, of course, helps with the downstream task. So we did 2D SLAM. So basically, we have a depth estimate. We create a overhead view of the map and then merge them together with a robot trajectory. And if we don't have adaptation, the blue map, which is created by the robot online, kind of deviates from the ground truth a lot. But after adapting to the noise, we can have a better map. It's still noisy, but we have a better map. And the localization performance and the mapping performance numerically also gets better. Okay, so if you use panoramic image for getting a 3D context, I think it's very lightweight and efficient way, and we can make it usable or less noisy by applying some depth estimation network with a fine tuning for the current setup. Okay. So yeah, I think that's all of the small projects that I wanted to talk about today. And I was also very ambitious, and I was also expecting more catalog. And I also have one slide per other projects, so you might get a peek of what's going on in my lab. So it's a completely different topic, but I outlined the projects as a generation and reconstruction. But I think what is more interesting is actually interacting with the 3D world. So what's upcoming is more related to interacting. So by interacting, we are talking about robot manipulation, robot navigation. We had a little bit of navigation at the end, but robot navigation. We also have many people working on human object interaction. So I'm gonna have a brief overview of that. So one is, so this is again navigation network and navigation work. And we are having a similar idea here as a previous project. We want to quickly adapt the current mapping agent so that we will better handle the current noise setup, which was not observed during training. And here we use the overhead map of the estimate, and we use style transfer network here, because the styles of noisy estimate was clearly very noisy and blurry, whereas clean maps have a clean walls and so on. So we just use a stylized network to have an estimate of cleaner version without ground truth. We just estimate cleaner version and enforce the consistency between cleaner version to have a self-supervision to quickly adapt to the current noise, and we have a better mapping and localization accuracy. And we also have an ongoing work which try to build the 3D scene graph with RGBD sequences, and we also try to extend this into dynamic scene graphs, and hopefully it can be also combined with the other downstream tasks. And we also have students working on human motion generation. So there are some works which try to position human or like have a just two-person interaction, but combining everything together is not easy. So we want to have multiple humans interacting with each other and have a dynamic sequence of motion on there. So there are students who are working on this. And we also have another student working on building a good latent space of motion, like a foundation model of motion. We use a large database of motion and have a strong latent space and have it as a teacher network, and then use a student network or like lighter network, try to adapt and utilize those latent space to estimate the motions in noisy sequences. So that's kind of the results that we are getting, and it's currently waiting for the publication. And this one is gonna appear in SIGGRAPH this year. So basically, we have a kinematic motion capture data, which has a joints information, but it is very hard to get the subtle information in hand. So for hand, we utilize, we have a gym, by say interaction gym, and then train a simple task with simulation, physics simulation. After having this training, we merge them together with a motion capture and have perform the task in physical simulation to something that it's crucial to have actual hand grasping, tight hand grasping. So we could, for them, climb the rope or like pull the wagon, something like that. Yes, that was the idea. And we also try to do unsupervised object discovery and try to run RL on that. So it's called like a word model for the robot manipulation. And this work requires lots of GPU memory. So progress is kind of slow, but still we are pushing toward this direction. And we also have another student who is working on transparent object grasping, because transparent objects have very different performance for like a detection or segmentation, or it doesn't get really reliable depth estimate. And this one was published in ours 2022, but we also have another version which does a 3D reconstruction of a transparent object and try to grasp them. So yeah, so this is really the last slide. So I'm really interested in spatial AI, so we can perceive and then perform actually interesting tasks as necessary. And I think we are living in very exciting moments because those ideas has been around for a while, but things really started to work these days. So I think there is going to be great future in next 1 or 5 years, and we are among them. So I think that's very exciting. And I'd like to thank my funding agencies and my students.
I think we do have time for a couple questions. So, yes.
So much. That was amazing. I just want to, I would love to take the virus 985. So is this similar to the principle of knowledge distillation where we have a teacher network and a student network?
Yeah, so we are applying knowledge distillation for teacher network and student network. Is that like, yeah, so we are directly using knowledge distillation.
Yeah.
For project 6,
What is project 6?
I think it's the one where you mentioned it's very memory intensive. Could you briefly
That one?
Yeah.
why is that?
Because we are building, try to decompose individual objects without any supervision. So you just take a look at bunch of images and try to separate it to different objects and have a latent vector for that, and also try to encode those interaction between them. So there are some work who does this kind of thing, but they do with a very clean background with a very distinctive color objects in general. And even for that, it takes really long time to train for that.
So is it because of the long time horizon, or?
The time horizon they are handling is also very short because of the memory issue. So I think this is because
So is the memory size from the time horizon, or is it?
time horizon, and also we have a different slots for different objects, and we have a time horizon, and yeah, both of them. And this student is ambitious and he wanted to increase the time horizon to over any of the existing work, and he wants to have it all 3D and model non-deformable objects as well, in addition to rigid object, and that really complicates.
So one quick question. For the submitted work, do you have them all online?
We usually make it online after it is approved for publication in general.
So
But-
you can-
Oh yeah, sure. I mean, we can have inside the paper.
Okay.
Yes.
I'm curious for the panoramic info with the sphere constraint. I was wondering, so for when you said things are in infinite distance, like the sun and the clouds
Yeah,
and
yeah.
everything, since we are making it like kind of like an outer plane on the outside, would moving through that scene make it look kind of Hollywood backdrop like, where the clouds are kind of moving faster than they should be if you're moving in the sea?
So by infinity, we really mean that this is really, really, really large in numerical. So hopefully it doesn't create those kind of Hollywood sign like artifacts almost over those distance we are. If the distance is smaller, then it will probably introduce artifacts, but we assume those cases when it's really, really infinite.
So for the text to scene project, if I'm correct, or my understanding is correct, you optimize the textures for each individual object, right?
For detailed stylization, yes. For
Yes.
base color assignment, we are.
So then you would require bounding boxes to, or somehow you get the information for each structure of the each object. And what if there are two beds in a room? Then
Oh,
what?
it still works, because our part detection kind of figure out what is at the top versus what is at the bottom. I'm not sure what I can throw there.
It's quite far back.
Yeah. So there was also an example in the paper. Oh yeah, I already passed it. Yeah, in the paper where we intentionally put a book on a cushion, and they have a different part segments, so we can.
I know what I mean is in a scene there can be two beds.
Oh yeah.
Different beds, would they be stylized similarly in the scene or?
That we don't explicitly control, but hopefully we can get some similarity with the same image guidance and text guidance. So that's kind of weakly binding the different offsets. Oh, this is just our rendering. We already have a color and mesh, and we can put light anyway. And then we found that this rendering looks better in our own case.
Okay, if there are no more questions, let's thank the speaker again.